तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we saw the concept of digital system design using the approach of top down methodology, wherein the design was partitioned into architectural functional block or data processor block, if you will, and then the controller. And we said that functional blocks are generally available components either as individual IC parts or in the case of an IC design Verilog codes, and the controller is the one you develop based on the specification of the problem, specific to the customer needs or specific to the problem which is being the system being designed. And in that we said the best way to go about designing controller is to draw what is known as an ASM chart. ASM stands for algorithmic state machine, and we started setting out we set about to start design process with a simple example with this bus orbiter, wherein there is a bus which is available, which will be requested by two units called A and B. So, whenever the unit A requires the bus, it gives an RA signal as input to the bus orbiter, and whenever system B requires the bus, it gives a signal RB. The orbiter takes the decision on which of these two get the control of the bus, that is indicated by the signal GA being the ground signal for A, GB being the ground signal for B, and we are not showing the rest of this in how this enables the bus, how GA goes and enables the bus for A and how GB goes and enables the bus for B, all that I am not showing. It is only the simple design here. You see, normally only one of these requests come, it is either the unit which requires or requests the bus gets the bus. The problem or contention comes only when both the units require the bus at the same time. So, we have prioritized GA as higher priority than GB, RA has unit A has having higher priority than unit B. That means if both RA and RB come at the same time, RA gets preference, that means the bus is given to unit A or GA is generated. But if RB comes earlier than RA, even if RA comes before the unit B has completed the transaction, still it has to wait for the transaction of B to be completed. So, basically what it means is the unit which requires the as a time function, if you draw the signals, if this is where RA and if this is your RB, even though RA has higher priority than RB, since RB comes first, RB gets the bus and then it has to wait for the RA has to wait for the bus to be released by B before it can get the service. Before it can get the service. And also we assumed in this, to make this design simple, that the signal request signal is held for as long as as long a period as you want the bus to be available to you. That means if you remove the signal RA request signal A or B, the bus is disconnected. That means if the unit A requires the bus for a particular duration of time, for that entire duration of time RA has to be available, the signal has to be held high, RA has to be held high for that period. With this we do the ASM, this was drawn yesterday, this is for the last lecture, just for review, we have already drawn it. We have a state called idle state where both RA and RB are monitored. If RA is true, naturally it gets a preference and GA is generated, and GA continues to be generated as long as RA is true. Only when RA is false, it even goes and looks at B. It means as long as RA is true, it goes to several clock cycles during which GA continues to be generated. That means CA is available for the entire duration for which RA is true. After it is done with that, it goes and checks if if B also requires the bus. If yes, it goes and grant B signal and again holds it for as long a period as RB is held high, and when it is done, it goes back and again checks RA in between. RA could have asked for a request, one more request, and that will be again tested. If there is no such request, it goes back to the idle state. Similarly here, when RA is done, if RB is not requested, that means unit B does not request the bus, it goes back to the idle unit. This ASM we drew in the last lecture. I want to draw your attention to a couple of points here, which is a convention, more a convention than any concept or theory. The ASM is drawn like this, as I said, rectangles and diamond boxes, and then the within what you have inside is the signal. Here there is no signal in the ideal state, so there is nothing inside here. What you have is the state name, the box name, state idle state, GB grant B state, GA grant A state, and always an arrow. You always draw arrows. Arrow going to this, arrow going out of this, two arrows should come out of this, like this. So always arrows are put, and also it is a convention to draw true or false. So of course there is nothing wrong in saying 0 or 1, but generally in ASM, the original concept of ASM drawing of ASM, decision boxes always have two paths in the output. One is called the true path, the other is called the false path. So it is a true or false usually, same as 0 and 1. As I said, it is only a convention. It is better to follow conventions when you draw a chart. But the next step is to implement it in hardware. As I said, this is nothing but a state graph. You can think of this as a 3-state graph with A, RA and RB being inputs, G and GB are outputs, and under different conditions of RA and RB, they remain they go to different states and give different outputs. So we know how to do that, but we will not redraw the ASM, the state graph, because we know how to implement a state graph into hardware. For that reason, we will not draw this again to state graph. Actually, we said the advantages, easier, elegance, etc. for ASM. So we will see how to directly translate or map this ASM into hardware. That is what we will do next. That is implementation of ASM. Before we do that, we have to assign states, same logic or same concept as the state graph. There are 3 states, so you need 2 state variables. We will call them x and y because A and B have been used here. So I will call the state variables x and y, and I will arbitrarily assign the state 0 0 for this, 0 1 for this, and 1 0 for this. or 1 1 for this, does not matter, and it is always again a convention to put a circle around the states. The state assignment, as it is called, is marked outside the box on the right hand top and enclosed in a small circle. This is a convention again. So, there are 3 states: idle state whose assignment is 0 0, GA state whose assignment is 0 1, GB state whose assignment is 1 0. So, state assignment. GA state, GB state, x and y are being the state variables. So, similar to state graph, you draw ASM table. So, first step in implementing ASM chart is to assign the state variables, state assignment. Once you do that, you go for the ASM table. So, we will have to see what is the present state and what condition leads to what next state, and what outputs are generated in that state. This will be the columns of a ASM table. I should have written it like this: ASM table. There are 3 present states: idle state, present variables are x, y, next state variables also x, y, and we know that in order to differentiate between this present value and next value of x and y, we put x plus and y plus. This is a convention, we do it in when we follow even in state graph implementation. So, we do not give the conditions, we write the condition rather than all the input here. So, idle state is 0 0. What are the different conditions under which it goes to the next state? Now, here if your idle state RA is true, it goes to GA. If RA is true and RB is false, it goes to state GB. If RA is false and RB is also false, it goes back to idle. All these 3 conditions, all these 3 paths have to be represented in the ASM table. So, the ASM table will have one row corresponding to each path from a given state to various next states. So, this state has 3 paths leading to 3 next states. Of course, one of them may be same state or 2 of them may be same state, does not matter. As long as there is a path out to another state, you have to put a separate row for it. So, there are 3 rows. First row is RA true. So, I will put here RA. Second thing is RA true and RB, RA false and RB true. So, RA bar RB. Third condition is RA and RB both false. So, under the first condition it goes to GA state, which is nothing but 0 1. Second condition it goes to GB state, which is 1 0. Third condition goes to RA RB both 0 0. That is the idle state. So, I have finished all the transition from the present state idle. All the like that you have to draw for the, you have to list for all the present states and the corresponding paths leading to the next states, various next states. And what is the output here? In none of these paths there is an output, because we are in state here. The output corresponds to the present state. The present state is idle state, and idle state there is no output. So, there is no output, no output, no output, no output. So, we can quickly complete this table. The next state is GA, which is 0 1 state. How many paths are there here? There is a path. If RA is true, it goes back to GA. RA is false and RB is false, it goes back to idle. If RA is false and RB is true, it goes to 1 0. So, first thing is RA true, second thing is RA false, RB true, third is RA RB both false. In first time, in the first case, first instance it goes back to GA, second instance it goes to GB which is 1 0, in third instance it goes back to ideal state which is 0 0. Completed the job. What are the outputs? As long as you are in state GA, the output is GA. That is it. No questions asked, because no conditional outputs in this ASM. All the outputs in this ASM are, yesterday I talked about conditional and non-conditional outputs. In a conditional output, you will have a output at the output of a state based on a condition being true. It is given by a elongated bubble. Whereas in an unconditional output, this is the output where the output is related to the state in which it resides. Output is marked within the state. So this is an unconditional output or a Moore output. So output is always GA. All the three states will have, all the three paths will have GA output. And finally, the GB state is 1 0 state. It has again three paths. Go back here, go into this, go into this. So if GB, if RB is true, it goes back to the same state. If RB is false and RA is true, it goes to 0 1 state. If both are false, one 0 state, 0 0 state, and in each of these paths or each of these rows, output is GB. Again, this is conceptually it is not different from state graph. ASM is not conceptually different from state graph. This table is not conceptually different from state table, but the way in which you write is slightly different so that it can directly be implemented. This I said is drawn this way so that we can have a direct correlation of the hardware that we have in mind. The signals coming, activating and giving outputs. Signals come, the transitions occur based on signals, outputs occur based on signals. That concept is directly seen here. Here you can see this table directly, it gives you the sort of a hardware implementation. That is all. Otherwise there is no conceptual difference at all. Once you have a state ASM chart, you can also draw it as a state graph and finish your design as you have done. Otherwise there is no going to be any change in hardware or anything. Now since we know several methods of implementing state graphs, we have seen all of them, we will use the simplest and most elegant method, maybe namely the multiplexer based approach. So I am going to do a hardware implementation of this using multiplexers. So what is done is there are two states. Each of the states requires a flip flop. Is it not? I wanted to recall the lectures on multiplexer based design of the sequential machines. So we have X and Y as two states, D flip flop. So the input to the D flip flop I will call it DX, X flip flop. Input to the D flip flop correspond to Y I will call it DY, and both are run by a clock. This is system clock. This clock has to be shown in the part of the block diagram. The first time I drew this to draw the ASM, I did not show this because I only gave the specification of the problem. RA and RB are two input signals, GA and GB are two output signals expected, but then strictly speaking you should have included a clock. That is why today I remembered to put a clock also in this. Clock is an input that has to be shown always because clock is required. The final implementation requires a clock, so a clock has to be shown here because as you see here the clock is already there. Now how do you drive these flip flops? Using multiplexers. And since there are 4 states maximum, of course there are only 3 states, but maximum 4 is possible. So you use a 4 to 1 multiplexer here, 4 to 1 mux. correspond to dx, another 4 to 1 mux correspond to dy, and the inputs to these muxes come from the conditions that we impose for changing from state to state. So, correspond to each state, the multiplexer selector outputs, selector inputs are decided by the present state, and the next state is decided by the input that you give to the present state. For example, here x and y are two variables corresponding to the now when we are in present state, ideal state, which is corresponding to state variables 0 0, assignment 0 0, what condition will make it go to 0 1, what condition will make it to 1 0, what condition will make it go remain in 0 0. This is what you have to see. So, what we do is we look at one flip flop at a time. We have done this before, I am just reviewing this. So, we will do it quickly. So, first we look at flip flop DA. Flip flop, this is correspond to flip flop A, I am sorry, dx, not DA, flip flop X, and this column corresponds to flip flop Y. So, when the present state is 0 0, x is 0, the only condition under which x changes to 1 is RA bar RB. The other two conditions, x remains 0. So, x remains 0 here, x remains 0 here, but x changes from 0 to 1 here. So, I will have to put here RA bar RB as the input to this, which will, if the condition is 0 0 and if RA bar RB comes here as the input to this, then the flip flop has to change from 0 to 1. That is the concept. So, we look at this second. Again RA bar RB, I hope I am not making a mistake, please tell me if I make a mistake. So, again it is RA bar RB in state, in the second state, which is 0 1 state, the only case under which the output becomes 1 is when condition RA bar RB occurs. And the last thing, the present state is 1 0, the change is the x will, next state x is 1 for RB condition, for other two conditions is 0. So, I put RB here, and this is not used. So, it is the NC, no connection, or you can put a 0 or a 1 to be safe. If you want to be 0 0 to be safe, you put a 0. So, in case something happens, it goes to the reset state, ideal state, and waits. Similarly, I can quickly do this for the second flip flop. Y condition RA leads to the next state being 1 for flip flop Y. Here again RA leads to, the design is so simple as you see. RA leads to the next state being 1, here RA RB bar leads to the next state being 1, this again I will put 0, so that any false inputs you will end up in 0 0 state. Of course, this can be implemented using gates. This is a 2 input gate with an RB bar and all that. So, I do not want to show all that. You can draw a gate for this with an inverter B input, RB input. Here you can draw a gate with an inverter RA input, and the same output can be used for these two. So, there are only a couple of, one gate here with an inverter, one 2 input AND gate with an inverter, one 2 input AND gate with an inverter. So, totally two input AND gates and 2 inverters will do the entire design here. And the output is now tied to states, that is makes it easy. So, in state 0 0 there is no output, state 0 1 the output is GA, state 1 0 the output is GB. So, what we do is normally to make the design simple, even though it is a little more expensive in terms of gate count, already we have talked at length about reduction of the number of ICs compared to the reduction number of gates, and how the reduction number of ICs is more economical and practical solution, especially today in terms of IC design. So, I will use a 2 to 4 decoder, to which I will give this x and y as inputs and get 4 outputs. This is my 0 0 output, 0 1 output, 1 0 output and 1 1 output. So, the 0 1 output corresponds to GA and this corresponds to GB. So, the design is completed. 2 muxes, 2 D flip flops, 1 2 to 4 decoder, 2 2 input AND gates, 2 inverters. But more than the hardware list, part list, which is I am not very concerned about it, the ease with which you can do the design. Once you have the ASM, it is almost a translation, hardware translation if you want to call it that. But that is what makes it more popular approach, ASM based approach. There are other ways in which you can do it. I can use a ROM. Once I have a table here, I can now implement this table. It is only a truth table, basically it is a truth table, implementation of a truth table. I can do it using, all I have to make sure is the outputs have to be given here, x and y, x bar, x plus and y plus are the inputs to be given to the D flip flops, which drive the flip flops to the next state. So, we can think of this as a combinational logic with different conditions, and I can implement it using ROM. I can also implement it using PALs. All these things we have seen earlier, so I am not going to do this. So, I will leave it as an exercise for you to complete the design using, complete the same design using a ROM in place of, okay, I will not say in place of, because an ROM requires an external flip flops, PAL does not require that because PAL has flip flops output. So, PAL will take the whole thing into one IC including the flip flops. ROM will require the combination logic alone, we can replace by a ROM. We still require 2 flip flops and the output GB. Anyway, as I said, this I am going to leave it as an exercise since we are familiar with this. Even in earlier courses, plus we have also done a review of this in the earlier lectures. So, to just summarize then the approach of ASM based design, we have this partitioning technique where you have a top down approach. You look at the problem, identify how it can be partitioned into functional units which are available, we do not have to design them, but choose them such that they are available readily, and also choose such that we have enough controls. If you want to clear a register, you should have a clear control. If you want to increment a register, you should have increment inputs. So, these are things you have to look at, and then once you partition the problem, you get all the signals input and outputs required for the function units. Then go to the controller, find out what are the external inputs and outputs required, and then use these inputs and outputs from the function units and identify a clear block diagram of the ASM or the controller. And once you have that, you go to the ASM chart, and the ASM chart is the most critical thing because it has to be time wise, it has to be done properly. So, you have to time it properly. For example, this is an important step, I would say. RA has to be kept on, GA has to be kept on as long as RA is high. Supposing I did not put this, your tendency would be, the first time designer, the tendency would be, okay, I have RA true, give GA and then verify RB and then go back. That is what you would do first time. If I had done it, what would happen? RA would be kept on for a while, whereas I have, this is only one clock period. I told you every state the circuit or the system remains for one clock period. So, at the end of one clock period, it will test RB, it will find it is not true, it will go back. Now, okay, in this case I will put the problem in a slightly different way. Supposing RB is also true, RA will be given and then you will find RB true, so it will start giving GB. So, GA is not completed. So, there is only one clock period for a GA is available. second clock period GB will be available. That is wrong. I want GA for as long as RA is available. So, if I do not check this, only when RA is removed completely, as long as it is true, I will have to keep circulating this loop. This is a cycle concept, actually it is a timing concept here which is inbuilt into the ASM. In a state graph it is not that obvious, of course it is, you can interpret it if you understand, if you are smart enough, if you understand ASM, understand the state graph clearly, you can find out, okay, as long as it is in this state it is going to give a signal, so I cannot go out of this state, you can say. Flow chart you do not have that concept at all, in flow chart you will not know what is happening. In state graph with difficulty you can have that, here it is clear, that is why. So, once the ASM is done, the rest is easy, putting it from here to here, from here to here, user ROM or PIL, it is all straightforward. So, this completes the first example and a very simple one. We will take a couple of more examples in which we will try to introduce a little bit of complexity. We will see the next example now. In the second example of ASM based system design, we will take the familiar example of traffic light controller. Traffic light controller is an example which is used in different types of digital design, starting from gate level, using PALs, for state graph implementations, even for microprocessor implementations. So, we will take an example, but we have introduced some features which are slightly different from what you find in textbooks. It is not that they are more complex or anything, but just to tell you, to drive home the point that specification is very important in your design. Unless you understand completely what is required, you cannot choose the hardware and you cannot draw the ASM. Unless you draw the ASM properly, you cannot implement the circuit. So, as I was telling yesterday in my last lecture, the specification forms a major part, understanding of the specification forms a major part of the design effort. Another major part of the design effort is the ASM controller, but the other things are of course usually the standard techniques. So, with that in mind, let us try to understand this problem very clearly. This traffic light control, this traffic light is to be a controller for traffic light to be installed in a road junction. There is a main road and a side road. Normally, under normal circumstances, there will be traffic from left to right on the main road and from left to right as well as right to left in the main road, this way as well as this way, and a traffic coming from this side, from the right hand side, can turn into the side road freely without any light. Similarly, the traffic from side road to turn into the main road to the right, to the left, can also do so without any problem. So, what I am saying is, normally there is a green signal on both sides of the main road for the traffic in both directions, and the free left turn from side road and into the side road are also allowed. So, normal traffic flow is this way, this way, this way and this way, all at the same time. We are assuming it is a 4-lane road, there are enough lanes to take care of this. Now, but if there is a traffic coming from the left on the main road and wants to turn into the side road, or if the traffic on the side road trying to turn into the right into the main road, then we will have to be careful about the signals. So, the signal is designed for this type of operation. So, as I said, the first case main is green, we are going to call these lights M1 and M2, M1 for main road light in this direction from left to right, M2 for the main road light in this direction from right to left, MT for the traffic MT for the main road light allowed for traffic turning into the side road, and S for side light for turning from side road into the main road in this direction, and G stands for green or R stands for red, Y stands for yellow. That means main road is green in both directions. The first diagram here, M1G, M2G. The side road, the traffic into the turning MT is red. Similarly, side road here for turning from here into the main road is also red. So this side road is red, this turn signal is red, the main signal on both directions green, traffic will flow freely as well as turn into free left and free left. Then go to this diagram. We are assuming there are two sensors here, S1 and S2, which will sense the presence of traffic which want to turn into this road or from this road into this road. S1 will sense the traffic which desires to turn into this, and S2 will sense the traffic which desires to turn into this. So when S1 and S2 will be monitored, if one of these two is on, we have made the problem simpler by saying we don't have to verify which of these is generated a signal, S1 or S2. After a particular time, of course we cannot interrupt the main traffic too frequently. So a particular time has to elapse. After that particular time, if one of these sensors is active or generated a signal, we will assume that this is a signal requirement for turning from the main road into the side road. This is an assumption. Of course this may not be a justified assumption. The second sensor may be on, the first sensor may not be on, but we will also give a chance for the second sensor later on. Otherwise it becomes a little more complex. To make it simpler, we have made it like this. Whether S1 or S2 is on, we will assume first the traffic from main road to side road and then from side road to main road. In that sequence we will go. So we will go, this has to, first of all, before allowing the traffic to stop, we have to make it yellow. So this traffic can go on, and for this to go I have to stop this, and this cannot be stopped abruptly. It has to first go yellow. Here it was green, here it is going yellow, this continues to be green, this continues to be red, this continues to be red. Now after a specific period of yellow time, so that enough time is given for the fast moving traffic to slow down on this side, it becomes red. So the third diagram here, we will call it S3, the traffic will become red here, so that it will block the traffic flow through the main road, and this will become green. So the main road continues to be green and the turn also will become green. We have stopped the traffic from right to left. This traffic is always stopped anyway, side is red. Now this will be allowed only for a certain amount of time. We cannot allow the side road to go on being green, blocking the main road traffic. So after a particular time is elapsed, we will not worry whether the sensor is active or not. We will make it yellow, this continues to be green as I said, and when this is yellow again this has to keep red. This will be red, this will be red, this will be green, this will be yellow. After the yellow period, now we have two choices. If the sensor S2 is still active, that means a traffic or car is waiting to turn from the side road into the main road on the right hand side, we have to accommodate that. On the other hand, there is no car waiting, even though the original sensor S1 or S2, we decided one of these two sensors were on. It so happened that S1 was the reason for that, and there is no traffic waiting in S2. We do not have to unnecessarily go and waste our time trying to make a green for the turn from main side road to the main road right hand side. So we will here at this point we will only check S2, we will not check S1. S1 we have already given chance, it has to wait for some more time before it can be again tested. But I want to test, we will want to test only S2 now, and if S2 is off, that means no traffic is coming in this direction waiting for turning, we will go back to the original mode of this becoming green, this has already become red, now this red becomes green, so this will be green, this will be green, this will be red, and this yellow will become red, this continues to be green, this continues to be red, this red will become green. On the other hand, if S2 finds is on, that means the traffic is sensed, we have to let a chance, we will have to give a chance for this traffic to move into this right hand side. So, we will now go through a sequence where we will now stop both the traffic, even though originally when the turning from the main road into the side road, we let the main traffic pass without any break. When you are trying to make the same type of thing from going from side road to the main road, we want to be careful because we do not want the traffic going here carelessly going and hitting the main road traffic. We want to stop the main road traffic in both directions. That is again a specification we have made. Both here for the left turn, for the turn from the main road to the side road, the right turn, we will allow the main road traffic on this direction, only in this direction we will stop. Whereas for turning from side road to main road in this direction, we will stop traffic in both directions. This is one of the specifications you have to be careful about, remember this. So, we will make this yellow, this continues to be red, there is no problem, and then this is red, no problem, this was red, and now after this yellow, this becomes red, this continues to be red, and now we will make this green so that this traffic can go, this continues to be red. Allow for certain time to elapse for this traffic to clear, make this yellow again, continues to be red, this continues to be red, this continues to be red. After the sufficient time for which yellow is on, we will go back to the original mode, this being green, this being green, this being red, and this being red, that is this traffic. So, basically there are 7 different conditions, I have explained each one of them, we will also go through the state graph in a minute. And what are the hardware requirement, the functional requirement and the partitioning requirement, how are you going to make it? Again it is not a very, functionally it is not a big thing, functionally all we need are lights which are controlled. Of course light cannot be directly turned on by a digital circuit with very limited current drive, but we are assuming we are operating, we will have signals which will operate power devices which will give sufficient current for these lights to be turned on. So, the light will be like this fashion or Y green for each one of these, there will be one of these, each we will call it a fixture, light fixture. There will be a light fixture here for the through traffic, a light fixture for turning traffic, a light fixture for side turning traffic, and light fixture here for main road traffic. And only thing for the turn we will put an arrow in addition, there will be red, yellow, green, but this will be having an arrow in it. Here these are pure complete lights, simple lights, here these lights will have an arrow in it, so that we know there is a turning signal. And the timer is the one which is going to control. Now, we need to, whenever we want to time how much time the traffic should be on for the main road, how much time the traffic should be on the side road, how much time yellow should be there, all that will be controlled by a timer which is a single timer. We can start every time we want a timer, we can start the timer, of course it is clocking, so it will be a counter, simple counter, and whatever time you want you can tap it from here. These are non-exclusive, these are exclusive events, these are not mutually exclusive events. So, each of them there is no overlap between any of these intervals. As long as there is no overlap between any of these intervals, I can have a same counter which can repeatedly reset and start. Every time I start the timer, it will start from 0, and after a particular time is elapsed it will become yellow, after a particular time is elapsed it becomes TS, after there is a side road duration, light side road green duration, main road green duration, yellow duration, and these are, as I said, mutually exclusive. So, there is no problem about having a same timer do all of these jobs. A quick look at the state graph model to just for us to understand what is happening. This is the reset state, this is the reset state where we are waiting for where this timer has to be turned on, and then we have this, all these 7 states we have discussed there, all be here, 7 different conditions, S1, S2, S3, S4, S5, S6, S7 correspond to that. As I said, from S4 there is a way out to S4, if from S4 there is a way out to S1 if there is this sensor S2 is not on. If the sensor S2 is false, we do not go through S5, S6, S7, we directly go from here to S1. Otherwise, we will go through the full sequence of S7 and coming back to this. This is the ASM chart, again very simple. You wait in a state called the reset state, this is the start, the beginning, and you start the timer. Same nomenclature has been used, M for main, 1 for main from left to right, 2 for main right to left. So, M1, M2 are the two lights on the main road, this is right to left, left to right, this is right to left, T for the turn signal, S for the side signal. So, all you have to look at is these indicators here, M1, M2, MT, S will always be there in all boxes, green, green, red, red, green, yellow, red, red, like that you have to see. So, it will be first green, each of these states corresponds to one of those diagrams we discussed earlier. Only thing is, after each, this will be in this state until the main right duration is over. So, as long as main like duration is not over, or if one of these signals S1 and S2 sensor signals is not on, in either of these two cases you continue to be in the main road flow, green from left to right, green from right to left. So, M1G and M2G is normal mode. So, if S1 and S2 occurs before Tm, the elapsed of the main road duration we want for the main road minimum duration without interruption. We want uninterrupted traffic flow for a while in a main road. So, if after Tm one of S1 or S2 becomes on, then it goes to the second state where we go through the main road green, main 1 green, main 2 yellow, turning red again, it is a comma not a 1, and then side road. So, every time we go we start a timer, because here I have to monitor the yellow, here I have to monitor the Tm. So, I put a start timer, here I start timer because I need to monitor the yellow timing. Until the yellow timing is elapsed, it will continue to be in the state. If the yellow time is elapsed, we will start the timer again, go to the next state where main road green, 1, main 2 becomes red now, from yellow it has become red, that means the turn red, turn from main to right turn from main to side is allowed with a green signal, side to main is not allowed, it is red. Again this period is the duration for which we want the side light to be on, TS stands for the side road duration, light duration, and as long as it is not over it will continue in this state. It is over, again you start the timer, go to this, go to the main, again this becomes red, turn signal has to become yellow, and here red will be side to main will still be red, then again yellow signal will be monitored. If this yellow duration is not over, it will continue in this state, if it is over it goes to the next state. Here is where I introduce the concept of S2. If you do not want to check S2, you can go through the whole cycle without this S2, you can go to the next state. But if S2 is not on, I have completed the turning from the main road to side road, right turn, and if S2 is not on, that means no traffic is waiting to turn from side to the main, there is no need to go through the other states, I can go back to the original state where that is the most preferred state, because the main road traffic is the most important traffic. So, at S2 is false, we will go here, we have to start the timer here. On the other hand, if S2 is true, that means I have to go through one more light here, I make the main road yellow, main turn is already red, the second main, that is the right to left, is already red, side is continued to be red. So, yellow duration is monitored, until the yellow duration monitored, the main one remains yellow, after the duration you start the timer again, main road becomes red from left to right, it is already red left to right, that means both the sides the main road traffic is blocked, turn from main to side is also blocked, then the side road is free to turn from side road to main road, become green, the duration of that is Ts, again the duration for the side road turning into the main road is Ts, it is monitored, it is over, it goes to an yellow because you can't abruptly stop from green to red, it goes to yellow, main 1 red, main 2 red, main turn red, side becomes yellow, after the yellow period elapses it goes back to the original. Now this A is the continuation of the original. So this is the starting point, so this has to be connected here, since I did not have space here, now I can draw it like this. I did not want to draw it in the original because it would confuse you. Now the explanation is over, this point is same as this point. So, the ASM goes like this from here to here to here to here and go back to here with a provision to branch off from this point into the main. That is what is shown here again, S0, S1, S2, S3, S4, S5. So, the problem specification has to be clearly understood. If you want to draw diagrams for each one of these conditions, clearly identify the hardware required. It is very simple. In this case, hardware requirement is the lights and the timer. That is all you need. And once you understand the problem very clearly and identify what signals are there, start timer is the only input signal to the this functional unit, and TM, TS, TY are the only output signals of functional units. So, rest of the signals are inputs to the controller. Start timer and the time it starts, then you monitor TM, TS, TY. This is a command from the controller to the functional unit, the status of the functional unit into the ASM, and then the outputs are, all these are outputs, whatever you put inside. So, we have followed the same procedure. The problem is not really complex, it is a big problem, I would say. What is the complexity? This is a stiff, simple traffic light controller. Purposely I made these minor things unconventionally, that only one side state, free left is allowed in this case, traffic flow is allowed in one direction even when there is a turn on, the other direction traffic is not allowed. All these conditions I put for that so that you will completely understand the specification before you put your design into ASM. So, understanding the specification clearly is very, very important step. To just to illustrate this point, we have unnecessarily put some conditions which may not be really logical. That is okay, because as long as you understand the conditions and do the design. We will see the implementation of this using multiplexer based design in the next lecture.